Our next topic is arrays. And I'm very sure you have come across arrays in the past in math. Very likely you have seen subscripted sequences of numbers like this one. Everybody, right? Basically, that is already an array. What is the key feature that we have here? The key feature is not that we must always use literal values here for the indices. The key feature is that we can use a variable here for the index. So we can write something like a sub I, for example, and then we can write things like sum over all the I from 0 to n over the a sub I, for example. Yeah? And so that's the key feature that we want of these indexed sequences, and arrays are a way to have this in C++. I should say this, of course, is a one-dimensional array, and you've dealt with two-dimensional and three-dimensional and so on, and most likely even higher dimensions than that. So the chapter is structured as follows. There is an introduction to arrays, then there is a section on arrays in functions, and there is a section on programming with arrays, and last not least, there is a section on how to implement multidimensional arrays. So, the purpose of using an array is to process a collection of data where every item of data is of the same type. If you have a list of integers, whatever, a list of counts of turtle eggs in nests, for example, or a list of double values, temperature readings every morning of a day at 6 a.m. or something like that. A list of names, for example. All these items of data will have the same type. They will, so it's a homogeneous list of data, and we want to do something to all the elements. Whether that is, for example, converting temperatures from centigrade to Fahrenheit or the other way around, or checking that every first name and every last name starts with a capital letter, or summing up the values that we have, whatever it might be, we very often want to do something to all of the elements of such an array. And it should be obvious, but just for laughs, imagine you would not have arrays. Yeah. Now, if you need to keep track of 5 test scores, you might declare 5 separate variables. A variable score 1, score 2, score 3, score 4, and score 5. And now for getting those values from the user, you'd have to repeat 5 almost identical pieces of source code in order to get the data. In order to operate on the data, you'd have to write out the 5 names every time. If you want to write a list of those, you'd have to do a cout for each and every one of those variables explicitly in source code. Now that's okay maybe for 5, but now imagine you're dealing with 1,000. And then it becomes completely, completely ridiculous to do that. So this is where the arrays come in, because they allow us indexing based on a variable, and thus we can write one piece of source code that iterates through all the possible or all the indexes of interest. So, now you've seen this before, but we didn't talk about what it really meant. Now, if you write a declaration like this one, it says that you want to declare 5 indexed variables. Yeah? You're doing several things here at once, depending on what level we look at. At a lower level, you're declaring 5 variables at once. The same thing is said by saying you're declaring an array that contains 5 elements, 5 indexed variables. Just a different way of expressing the same thing. Once you have declared this array, and for terminology, so in the declaration, what comes between the square brackets is the size of the array. What is before those brackets is the array name. The type here is the type for every one of those indexed variables. Yeah. And now when I want to refer to one of those indexed variables, then I need to write something like this. I need to write score in square brackets 0, score in square brackets 1, up to score in square brackets 4. Indexing always starts at 0. There is no way to change this in C++. There are other programming languages that allow you to have whatever, an index range that goes, let's say, from 10 to 20. Not in C++, indexing always starts at 0. And so if I have 5 variables starting at 0, then the highest indexed variable will be 4. And yeah, arrays are used so frequently, and we need to talk about them so frequently, that there are quite a lot of ways to name these components that are involved in using an array. For example, this is called an index, or it's also called a subscript. It's also called a position within the array. So all these things are synonymous. What else? Yeah, so I haven't highlighted this yet or emphasized this yet, but let me do it now. The square brackets within the declaration and the square brackets outside of the declaration have 2 different meanings. It's like an overloaded operator, if you want. The square brackets in the declaration enclose the number of variables that you want. The square brackets outside of the declaration enclose the index that you want to use. 2 different meanings. Yeah? Important to separate those 2 different meanings. Okay, the variables that make up the array are referred to as indexed variables, as subscripted variables, as elements of the array. And you can see by the number of different ways that we have of speaking about these that this is something that is used quite often. Yeah. Otherwise, why would we have so many different ways of speaking about it? I've already mentioned this. The largest index is 1 less than the size, and the first index value is always 0. You can use array elements of any type. And when I say any type, I mean any type. You can have integers, of course, as array elements. You can have doubles as array elements. That wouldn't be a surprise yet. But you can use class types. You can have an array of input file streams, for example. If that makes sense in your specific application, let's say your program needs to open 20 files for input at the same time, and then somehow iterate over those streams, then you can do that with arrays. Yeah, so you can have an array with elements of any type. That type is called the base type of the array. It's the type of the elements. Yeah. And an indexed variable can be used anywhere where an ordinary variable, so not indexed variable of the same type, could be used. Yes, I think I've already mentioned that. Yeah. So that's the difference here again, the difference between declaring the size of the array and using an individual element of the array. Now I want to emphasize how the indexing works, because by understanding that, you will have an easier time later on when we talk about strings. In memory, the array starts at some position. So let's say this is our score array, and the name of the array, in this case score, can be thought of as a name for an address. So let's say the array starts at address 1000, just for the sake of simplicity. Then score refers to that address 1000 in memory. Now when I say score square bracket 0, in order to use a variable, an indexed variable of the array, what happens for the indexing is the following. Score. Take the address where in memory this array starts. Go 0 times the size of the base type forward, so do not go forward at all, and use the variable that is located at that position in memory. Yeah? So in the same way, if I say score 2, for example, then it would mean take the starting address of the array, go 2 times the size of the base type forward in memory, and use the variable that is located at that position. Okay. So that is how the indexing works. And of course, I can have indexed variables on the right-hand side of an assignment operation, and I can also have indexed variables on the left-hand side of an assignment operation. If you think about what I just said, take the address where in memory the array score starts, go n+1 times the size of the base type forward, and use that variable at that position. Use that variable at that position for what? For assigning 99 to it. So in this case, we would get the 99 here. Yeah? N is 2, n+1 is 3, so we have to go 3 times the size of the base type forward, 1, 2, 3, and that's the variable that gets the 99. Okay, and here's a match made in heaven. For loops and arrays, quite obviously, the for loops, if you have a for loop where you just use a counter, then it's easy to do something for all the elements of the array. For example, in this loop here, we have I as the loop variable that and the loop is iterated for the values in I from 0 up to and inclusive 4. And inside the loop, we output the ith element in the score array, and we output the string of by, and then max minus that score. So presumably, this is a maximum value of all the scores that we have already computed, and then we say how much this score is off from the maximum. And when I go to this display, you see a program that uses this. So here's the declaration of our array, and as you can see, I can declare such an array together with other variables that are non-array variables that have the same type as the base type of the array. Here's a loop that that allows the user to enter a score, and then it checks, is that score greater than the maximum that we have thus far? If it is, then that score becomes the maximum, and once we have completed that loop, the user has entered 5 score values, and max is the variable that contains the highest of those values, and then we can have this loop that we just discussed on the slide before. Watch out what happens here. We ask the user for the first, or we read the first score value from the user before the loop, and that is because inside the loop we need to compare to a max value. And if we would want to do all the input of those score values inside the loop, then how would we compare to a max? For the first value that the user enters, we wouldn't have a max yet that we can compare to. And we also couldn't set it to some default value, because if we assume that the scores can be all over the place, then picking any max value might distort the result, right? Okay, and here's one other thing to observe. This comment here. This comment here is very important, because, well, what does it say? It says max is the largest of the values, score 0, ... up to score I. This captures something that will be true whenever the execution passes through the end of this loop. Yeah? Whenever the execution reaches the end of the loop body, at the end of the loop body always, it will be true that max is the largest of the values, score 0 up to score I. This is called a loop invariant. Again, it's a comment, so it has no impact on the way the compiler treats your program. But it has an impact on your understanding of the source code when you ever get back to it. It reminds you of how the loop successively achieves what it is supposed to achieve. At the end, in the last iteration, I will be 4, and so this here translates to max is the largest of the values, score 0 up to score 4, which is the largest of all the values. Yeah, so this invariant here, it tells you, or it captures as a logical expression how you think the loop approaches the final result. In general, it is a good idea not to work with literal constants. With constants like 50 or 2 or 12. Because a constant like that, a numerical constant like that, does not convey the purpose. Remember when we talked about variable names, I told you that choosing a variable name, choosing it well, is an important issue, because it will make your program so much more readable if you choose it well. Well, values like 12 or 15, they don't tell you the purpose for which you want to use them. And in order to reflect this purpose, you can use named constants. So for example, if the room size is, let's say 17 or whatever, then introduce a variable, or better, introduce a constant, introduce a named constant called room size, and assign 17 to it. And from then on, whenever you would normally use the 17, use the constant room size. And that makes your program more readable. And it makes it easier to maintain it, because should you ever choose to do the venue in a different room that has a different size, there's just one position in the source code that you change, you recompile, you run the program, and you're done. You don't have to go through the program and check for, is the 17 used here? Is it used as the room size? Or is it used as whatever, the minimum age to participate in the course? Yeah. So named constants make your program more readable. Named constants are introduced just like variables, with only one slight difference. You put a const in front of it, where with a variable you would say int, then the name, and you could assign an initial value to it. With constants you would say const, then the data type, then the name, and then you must give the value. You cannot just say that this is a constant and not assign a value at the same time. And you can only assign this value once, right? After you have declared and defined this constant, you can never change the value, obviously, because otherwise it would be constant, right? It would be variable. Okay. And then you consistently use the named constant where the constant with this purpose was previously used. So for example, if you need to have one score for every student and you have this constant number of students, then you declare the array score to have a number of student elements. And then when you want to write a loop that iterates over all the scores for every student, then you make that loop iterate from 0 up to less than number of students. Okay. You cannot declare, well, there are some extensions that some compilers support, but you cannot rely on the possibility of reading a value from the user and then declaring an array to the size of that variable. Yeah? If in doubt, write your program so that the size of the array is known at compile time. The size of the array here is not known at compile time because the user has a chance to enter that size at runtime, and then the array has to be created to that size. Okay, the general syntax is the base type, the array name, and then in square brackets the declared size. And yeah, and then you have the indexed variables that are referred to by array name in square brackets 0 up to array name in square brackets the declared size -1. Yeah. I think we've already gone over this when I drew you that diagram. What the compiler needs to know, or what the compiler records of your array, is where in memory the array starts and what the base type is, so therefore how large each array element is in memory. Now here's some, well, pretty soon I'm going to have some bad news, not quite yet. If you write something like this, int a in square bracket 6, it reserves memory for 6 variables of type integer. If we imagine that every integer is stored as a 32-bit value, so that would be 4 bytes, so every integer would take up 4 bytes. So really, the memory addresses would increase by 4 for every array element that we go forward. We do not need to record the addresses in memory of the subsequent array elements because of the way I told you that the indexing works. So since they're assumed to be, since they are always in subsequent memory locations, it is enough to record the starting address and then to compute which address has the indexed variable. Okay, this is the piece of bad news. There is no bounds checking. What that means is if you access an array element that would be outside of the declared size of the array, then it's your problem as a programmer. There's no net. There's no safety net. So if I have declared score to be an array of 5 elements, and then I write in my program something like this, accidentally, that's a mistake that's frequently made by beginners, right? Just because the array is declared to have 5 elements does not mean, I mean, it precisely means that there is no element at position 5, because position 5 is already the 6th position. Okay, so what would that do? The compiler would translate this to instructions to fetch or use the variable that is, well, take the starting address of the array, go 5 times the size of the base type forward, and use the variable at that point. The variable at that point happens to not be part of the declared size of the array. So it is highly likely that that memory location is used for another purpose. If it is used for just another variable, just another integer variable, for example, then by, for example, storing something into this location, you're losing that other value, the value of the other variable, without knowing it. So very likely your program is going to produce garbage results. If that memory location should happen to be used for example, for a return address that the program, when it runs, uses to get back from a function call to the calling function, then you're destroying that return address. So the program will try to return to a memory location that very likely isn't even a location in your program, so your program would crash. So there are several options what could happen. The bottom line is the way your program behaves after assigning something to an indexed variable where the index is out of bounds, the behavior of your program then is undefined. Yeah, it can do anything. It can produce garbage values, it can crash, it can appear to run normal because, well, maybe you're overriding, maybe you are overriding a variable, but maybe your program takes a path in its execution that never uses that variable again. So there might not even be any harm done by it. But yeah. Okay, what's here? Yeah. Okay, and this is silent, right? This is silent in the sense that unless your program crashes, you will not know that this has happened. Yeah, this is another example like the one I just mentioned. Here we have an array that has 6 elements, so the valid indices are from 0 to 5, and we are assigning something to index position 7. We're assigning a value there, and that's exactly what happens. So we're overriding a piece of memory, a memory location that is not part of the array, but we're overriding it as if it was part of the array. And anything can come from that. Another thing that I didn't mention that can come from it, it might also be that you get that your program is terminated with a runtime error right away. If, for example, that memory location that you're now accessing is not part of the memory that was allocated to your running program. If you would access a location that is outside of the memory area that was allocated to your program, you get something that's called a segmentation violation, and your program is terminated right away. Okay, when you're working with arrays, just as with other variables, initializing the variables is often something that you want to do. You can do it like this. Declare the array and then set each individual indexed variable to its initial value. With an array that has 3 elements, this takes 4 lines of code. You can achieve the same by using this notation here for initializing the array. And then have it in one line. There is a rule about default values. So if you have an array that has been declared to have 10 elements, and you're initializing it with an array literal here that has only 2 elements, then the first 2 elements of that array will be initialized to those values, and all the remaining ones will be initialized to 0. But if you don't initialize an array, then the indexed variables are not initialized. I mean, there are apparently some compilers who do that. But the normal rule for C and C++ is that if no values are listed in the array declaration, then none of the variables are going to be initialized. That's the rule, the general rule. Some compilers might deviate from that rule, but yeah, the rule is this. And the easiest way, or the shortest way to make sure that all the elements are initialized to 0 is to initialize with curly braces with 1 0 in between. That initializes the first element to 0, and then by the rule that says that all the other elements are then going to be initialized to 0, you have initialized all of them to 0. Okay, so do you think that you can tell me the difference between a square bracket 4 and int a square brackets 5?
Int a square bracket 5 is the declaration of a.
Is the declaration? Yes.
Array, and a4 is the position of the number you're looking for, so it would be the last number in that specific array.
Yes. Very good. Yeah. So this is the declaration. Int a5 and a4 is using the variable. Okay. How about this? Do you think you know what the output of this code here will be? Symbol is an array of 3 elements initialized to these characters, and then we have a loop here. You think you know what the output will be? ABC. Exactly. Yeah. That was too easy. Okay. Any questions or doubts at this point? Okay, now we go on with arrays in functions. by the rule that I told you that any indexed variable can be used where a non-indexed variable of the same type can be used, it is clear that if I have a function that takes an integer, that has an integer parameter, then I can pass an indexed variable as long as the indexed variable has a type int, as long as the base type of the array is int. Yeah? I can pass such an indexed variable as an argument. That works even with call by reference. Yeah? If this would be int ampersand n here with a call by reference parameter, then I could pass an indexed variable as an argument, because an indexed variable is a variable that could be modified from within the function body then. Okay, and obviously it doesn't only work with constants for the indices, it also works with a variable. It actually works with any expression that will result in an integer value here. So we can even compute where we want to access. I times 2 plus 1, for example. Yeah. Okay, here's a program that illustrates this, the use of indexed variables. There's a function called adjustDays. We're using a named constant number of employees, only 3 for the moment, small company. The adjustDays function just returns old days plus 5. It's down here. AdjustDays gets a parameter old days and just returns old days plus 5. So, but here we're using number of employees as for the declared size of the vacation array. Then we have a loop that loops over loops number of employees times over this loop body. The loop here uses 1 up to an inclusive number of employees. That's still number of employees iterations, just that we start counting at 1 and we count up to and inclusive to number of employees. Sometimes it's more natural to do that, in particular when we think about people and we think about the first, the second, and the third. It's sometimes more natural to start the counting at 1, even though we would have to then map it to the indices by subtracting 1, map it to the proper indices by subtracting 1. But sometimes it's just more natural to think about it in terms of 1 to 3 instead of 0, 1, 2. In particular, when a loop has to produce output to a user, speaking of the ith employee, for example, enter the value for the ith employee. And if there's more code that would have to interact with a human user, as there is code that actually does the indexing into the array, then it would be natural to let the loop run from 1 up to an inclusive, in this case number of employees, and then subtract 1 whenever you have to index. Okay, but we can also have a loop that goes from 0 up to non-inclusive number of employees, like we do here. And then here, for example, number starts at 1, goes up to an inclusive number of employees, and it outputs employee number. Yeah. Obviously, if we would let it run from 0 up to a non-inclusive number of employees, then we would have to output number plus 1 here, and then not do the minus 1 here. So it's a trade-off. Yeah. So what we just talked about is using array elements together with functions as arguments to functions. But how about passing the entire array to a function? That is possible also. We can pass the entire array to a function. It's neither a call by value nor a call by reference, really. But it's actually, the bullet point here says it behaves much like a call by reference parameter. I disagree. It behaves much like a call by value parameter, just because it uses some indirection, you'll end up in the same locations. I'll explain what I mean by that in a moment. Let me quickly glance at the next slide. Yeah. So in order to have an array parameter, this is what you would declare for your function. So here we have a function called fillup. The purpose of this function is to fill an array, ask the user for this many values, and enter them one after the other in subsequent locations of the array. So the important part is the square brackets. They indicate that A is an array. There is no size here in that declaration, which means that the function fillup can be used with arrays of any size, and we pass in the declared size of a specific array that we have through this additional parameter size. Yeah, that's a design decision for the C++ programming language. Functions that have an array parameter, the array parameter doesn't have a fixed size. The alternative would be to not have the size here and instead have, say, a 5 here. Then you'd have a function fillup that can be used only with arrays of size 5. As soon as you needed to fill up an array of size 6, you'd have to write another function. Doesn't sound like a good solution, right? Okay. Now, let me talk about how this works internally, or what happens here. This parameter A to a function fillup is a variable and when we call fillup like this, when we call fillup and we pass in the array score, passing in the entire array just means that we use the name of the array without any square brackets for selecting an element, and by that we pass the entire array. What I've also told you is that the array name to the compiler is just a name that represents a location in memory, right? So what happens here, what happens by this call is that a parameter variable A receives this address 1000. That is what happens. So this array parameter is a bit different to an array that we declared, in the sense that the array that we declare in our program is assigned a fixed memory location by the compiler, and then whenever we use the name score, it represents this address. When we have a function that has an array parameter, we have an additional variable in memory that will be assigned with a starting address of the array with which the function is working. Yeah. But then what happens when inside the function we would write something like this? When inside the function fill up we would write a indexed with I. Well, what would happen is that since a was declared to be an array parameter, the content of a is used just in the same way as the starting address for the array score was used. So we take that content, we take that address, and we go I times the size of the base type forward. And the base type is known because the base type is this here, right? Yeah? So in a way, this is like a call by value parameter, because I can actually inside this function fill up, I could, if I wanted to, change the parameter a. Not that this is anything that you want to do right now. We'll get back to that later. I could change it. So this is in a way like call by value parameter. It receives a copy of the address that score refers to. In the way that this slide that we looked at earlier intends, this acts a bit like a call by reference parameter, because since we have the address and we go through that address to the location where the original array is, the original array from the calling function, any change that we make to array elements through this function fill up is actually a change that we will see in the calling function when we return from the function fill up. Let's say we call the function fill up from the function main and we pass in score. Then when we return from fill up, we will see the elements of score changed. So it's neither purely called by value nor is it purely called by reference. That's for sure. This is called by array. Okay, here's a possible implementation for the function fill up. It tells the user how many numbers to enter and then has a loop that goes this many times, iterates this many times, every time extracting a value and storing it into A at position I. And from what I just said, this will go to these variables here from the calling function. Yeah, we talked about that already. Yeah. But from our discussion just now about how this works internally, it should be clear that when an array is an argument in a function call, an action performed on the array elements is actually performed on the array argument, on the elements of the array argument. Yeah? So if we pass the score array into the function fill up, and the function fill up accesses the elements of the array A, which is the array parameter, and it stores something into those array elements of the array parameter, then this storing actually happens to the elements of the array argument, which is the score array. Too complicated? No. Clear? Something you might need to mull over a little bit. Yes. What the function But what we pass to the function, if we pass just the array parameter, what we pass to the function, if we don't consider any other parameters yet, then from the array parameter, the function knows the base type and the starting address of the array, not the declared size. So if the function needs to know the declared size, we have to pass that declared size in as an additional parameter, like we did in the function fillup. Yeah. So the function can process arrays of various sizes. For example, we can have calls like this. If we have an array score declared to 5 elements and an array time declared to 10 elements, we can do these two calls to fill up, because the array just needs to be an array of int. Whether it has 5 elements or 10 elements doesn't matter, as long as we make sure that the function fill up doesn't go beyond the declared size. It is possible to pass an array in such a way that the array elements cannot be changed. It is possible to pass an entire array to a function and at the same time say that this function has no business changing the elements. For example, here we assume that the function show the world, its task is just to present some data to the user, and then we have an array parameter here that has a const modifier in front of it. What does this const modifier do? Well, the const modifier makes sure that if you accidentally assign something to an element of the array A inside the function show the world, then the compiler is going to treat that as a syntax error. The compiler is going to give you an error and tell you basically, the gist of it is you're assigning something to an array where you told me that that array is a const array and that the function wouldn't modify it. Why would you want to do that? Why wouldn't you? If that can trigger an error, why would you want to do it instead of just leaving out the const and allowing the function to change the values? Why would you want to do that? What's the benefit of, is there any benefit of using const? Do you see any benefit of using const here? The difference is the following. If I drop the const and I accidentally assign something to an array element inside the function body show the world, then I'm not going to have an error. The program is going to compile and I can run it. If I put the const here, then when I accidentally do that, assign something to an array element of the array A, the compiler is going to give me an error. And I won't have a program to run. So what's the benefit here?
That if you accidentally put a wrong number, you know?
Right, exactly. If we do make this mistake, if the function actually has no business in changing any of the array elements, then if I do that accidentally inside the function call, I've made a mistake. And if I made a mistake, I want to know as soon as possible about it. Yeah? If you have to fail early. If you make a mistake, you want to be alerted to it as soon as possible. That's exactly the benefit there. Okay. Of course, const is part of the function signature, of the type signature of the function. So it needs to be used in the declaration as well as in the function header above the function definition. Yeah, there's another consequence of using this const modifier for array parameters. If a function with a constant array parameter calls another function and it passes that array onto the other function, then that other function also must receive it as a const parameter. If it wouldn't, then that other function would be allowed to change it, but that would break the promise of the first function not to change it. That might have been a bit quick. We're gonna go over it in slow motion, or a little slower at least. I have an example here. Okay, let's say we have a function compute average, and we didn't make this a const array. So theoretically, at least, even though it wouldn't be necessary in a straightforward implementation, but theoretically, that function is allowed to change the array elements. Now, if I call a function show difference, or I define a function show difference, and that function show difference has a const array parameter. Now, the const array parameter is a promise. It's a promise this function will not change the array elements. It's a promise that you make to yourself, and you want the compiler to check whether you've kept that promise to yourself. Now, when you call compute average and you pass this const array parameter on to the compute average function that doesn't have a const array parameter there, then that allows the function compute average to change the elements. So this function here could actually change the elements, namely if this function does it. And the compiler cannot guarantee that this isn't the case. And so that's why you get an error. Yeah? So if this function here promises not to make any changes, any other function that it calls to which it passes the array parameter must also have that same promise not to change any of the array elements. Okay. We do have 2 hours here, right? We have a regular Wednesday program, right?
Yeah.
Just confused because my phone said something about the other section starting. Anyway, functions can return values of different types. They can return integers, doubles, chars. They even can return a value of a class type. So a function can return an input file stream, for example, or a string, or whatever. Functions cannot return arrays. It's one of the things that functions cannot return. Now, when we talk about pointers in chapter 9, that's when you will see a way to get around this in a way. Not entirely, but close. Okay, now we want to look at a program that produces a production graph. We have this fictitious company that produces plastic spoons, and they have different plants, and the different plants have different departments. They have whatever, plastic teaspoon department and plastic tablespoon department and plastic cocktail spoon department and whatever. What we want is we want a production graph in the end. We want a production graph that shows us the units produced by each plant. So the program will display a bar graph showing the production of each of 4 plants for a week. Each plant has separate records for each department. Input is entered plant by plant, and since every plant has separate records for each department, we're going to have to go through all the departments, the production for each department per plant. And output is supposed to show 1 asterisk for each 1,000 units, and production is rounded to the nearest 1,000 units. So those are pretty much the requirements. And again, the main purpose of doing this is to go through this whole procedure of developing the program. So, the first part is to analyze the problem. When we analyze the problem, we find that in the end, our output will show 1 asterisk for each 1,000 units. Production is rounded, and we want, what does it say that? A bar graph showing the production of each of 4 plants. So we want the total for every plant for that week, where the numbers of the departments have already been accumulated, summed up to 1 number. What that means is that we really need to keep inside our program only the production number in units. We don't need to keep records for each department in our program, because in the end we're not interested in the individual department's production. We're only interested in the overall production for each plant. So we can use an array named production that holds the total production for each plant. But just by that reasoning, if the requirement of the program were a little different, and it might force us to keep track during the run of the program of the production numbers for each department within each plant, then we couldn't just do with a 1-dimensional array. We might be forced to use a 2-dimensional array. We haven't talked about those yet. We will get to that later. Okay, so for the case study that we're working with, this is fine. We can do that with the 1-dimensional array. We can do that actually with an array that has 4 elements, right? Because we know that we have 4 plants. The program must scale these production numbers to the nearest 1,000 units to display asterisks in the bar, right? We want to have 1 asterisk for each 1,000 units produced, so we need to scale those production numbers down. Okay, so after this general analysis, let's identify some subtasks. Very often we can, these simple problems, we can very often split them up to just get the data, process the data, and produce the output. So that's the case here. Input the data, scale, that's the actual work that's done here, and then produce the graph, produce the output. So input data. How do we do this? Read input for each plant, set production plant number -1 to the total production for plant number, of course not n, but plant number. Yeah, so that's a typo here. That n must be plant number. Okay, and then there's a bad design decision here. For each plant, change production plant number to the correct number of asterisks. Why is this a bad design decision? What is the meaning of the array production? What is the meaning of one element, one individual element of the array production? What's the purpose? It depends. Before the scaling, the purpose of each one element of this production array is to hold the units of spoons produced by that specific plant. After the scaling, the purpose of every element of this production array is to hold the number of asterisks to print in the output bar graph. And that's the bad design decision here. We have a variable that changes its meaning, so to say, in mid-flight. Yeah? And that's always a bad idea, because that requires the programmer who is keeping track of what this program does to keep track of where in the program the variable is currently used in order to come up with what is the purpose of this variable at this point here and at that point there. A better idea would be to introduce another array called asterisks, yeah, and then to calculate the number of asterisks based on the production, the units produced, have two separate arrays, and then use the array asterisks to produce the output bar graph. And then you'd have two separate array variables, each with its own specific purpose, and that purpose doesn't change throughout the execution of the program.
So one array would hold the plant numbers, and the other would calculate the number of asterisks there should be.
Yes.
And you print out the asterisks.
Yes, you would use the production array to enter the production numbers. You would then have scale, which uses both. It's a function from the production array and produces the numbers in the asterisks array. And then you'd have the graph drawing that only uses the asterisks array. Okay. Yeah, the entire array will be an argument for the functions we write to perform the subtasks. We will also include a formal parameter for the size, that's clear. And we will use constants for the number of plants. And let's look at the whole code. So yeah, here's a constant number of plants. Then we have our functions with preconditions and postconditions. Input data, scale, and graph. The precondition to input data is that last plant number is the declared size of the array A. So that's the condition here. Postcondition is that for plant number starting from 1 through last plant number, A index plant number 1 minus 1 equals the total production for plant number. Since the records kept by those plants are kept for each department, that requires that inside this function input data we're going to have some kind of loop that allows the user to enter the production figures for each of the departments. Scale with its precondition and its postcondition, and then graph. Yeah. So the main function and so we must read all departments' data for each plant and add them up to produce the plant's total. The idea would be that we have a loop that goes over all the plants, and inside the loop we have something that will imply a loop also, read all the data for plant number, and sum the numbers and set the production array at the corresponding index to that total. So here's that loop. It makes a call to a function getTotal. That's another function that will produce the total for a single plant. And it has, we pass a variable here. This function has a call by reference parameter so that it can change this variable. And then, this is, not yet. Here. This is where this function getTotal is. So this is the function we just looked at. This is the function getTotal with a call by reference parameter sum. And the number of units produced by each department, append a negative number to the end of the list. So the user has a chance to enter values. As long as no negative value is entered, the user can continue entering values. So that presumably allows the user to enter the production figures for all the departments of a plant. And then just end the list with a sentinel value with -1 produced units. It outputs the total, and of course that total is then also stored in A of plant number -1. Okay, and here you see the program running. It asks for the data for plant number 1, and then the user enters, for example, 1, 2, 3 and a -1, 0, 2, 3 and a -1, 2 and a -1, nothing produced here, and then it outputs the total production for the plants, and it should output the bar graph. Well, we haven't really talked about the implementation of the bar graph yet. Yeah, as you saw on that other slide with the tests, the user who did this tested it with a plant that had some production figures, with a plant where one of the departments had produced zero units, where there was a plant that didn't produce anything, and so on, to check that all the different paths through the program work correctly. Okay, we have to look at an algorithm to scale. Remember, integer division by itself will not do the trick, because if, say, a plant has produced 4,999 spoons, and we divide that by 1,000, by integer division we would get 4. That would mean 4 stars, where clearly if it has produced 4,999 spoons, we would want to see 5 stars. So scaling implies rounding. Yeah, divide the value of a index by 1,000 and round the result to the nearest integer. If we assume that we have a function for rounding, then if we assume that we have such a function for rounding, then we can implement scale as a loop that goes over all the index values of the array and replaces each indexed variable, the value of each indexed variable with the rounding of that indexed variable's value divided by 1,000.0, and it should be clear why it has to be 1,000.0, because this is an integer, and if I divide by integer, I would have integer division, and I would already truncate the value, and the rounding wouldn't have any effect because I would have already truncated it. Okay. Have we talked about the function floor before? Floor and ceil? I think we did.
We discussed the functions, but never actually.
No, not the function floor. Okay, the function floor is a function to which you can pass a fractional value, and it will floor it. It will actually produce a double value, not an integer value. So it should be 3.0. That's a slight flaw here on the slide. It should be 3.0. No matter how close to 4 it is, as long as you don't reach 4, 3 point something, 3.99999, whatever, floor is 3.0. Obviously, in order to round, we can add 0.5 and then floor the value. So, because anything that is above 3.5, if we add 0.5 to it, we will be above 4. So the floor of that will give us 4. And anything that is below 3.5, if we add 0.5 to it, we will be below 4.0. We will stay below 4.0, and the floor of that will be 3.0. So that takes care of the rounding. And yeah, obviously at the bottom there's the function round that you want to test. Once you've tested round, you want to test scale in such a way that you do it with arguments that are 0, with arguments that need to be rounded up, and with arguments that need to be rounded down. So here's a program to demonstrate the function scale. It has a scale function in it. It has a round function in it. Round function is on the next slide. That's our round function. The cast is actually not really necessary because there is an implicit conversion from double to integer. So if we would just return the floor of number plus 0.5, there's an implicit conversion of the double result that we get from floor to int. But I mean, this makes it explicit, so you might as well write it to make it explicit. Okay, there's one more function that we need. We want to produce an output bar graph. It should be clear how to do that. We want to produce one bar for every plant. So we need to have one loop that goes over the plant numbers. And now, after scale, with the design that the slides propose, we have the number of asterisks in the production array. So we go over the production array, over the indexed variables of the production array, and for every one of them, we can call a function that produces the asterisks, that number of asterisks, as that variable says. And the complete program is in this display. I just want to show you the graph function now, because that's the only one we haven't really talked about yet. It's here. It has a const array parameter because it doesn't need to change anything in the array. And then it loops over the plant numbers, and inside the loop body it calls a function print asterisks with the corresponding number of asterisks. Okay, and then when you run the program, you get a nice little bar graph like this one. Okay, let's look at this. Can you write a function definition for a function called one more, which has a formal parameter for an array of integers, and increases the value of each array element by 1. Yeah, we're supposed to write a function one more that has an array parameter, and inside the function we increment every one of those array elements by 1. Think you know how to write it? Everybody? Okay, first of all, that should be clear. It's called one more. What's the return type? Does it need to return anything? Does it need to have a return type? Does it? It needs to have a return type. But which one? No. No. It's void, because what it does is it actually modifies the array elements in place. So by what I explained to you earlier, by passing the array, the function will actually have access to the array elements of the original array, of the array from the calling function. So what's the parameter? What's the first parameter? Huh. Not as easy as you thought, huh? Well, we has a formal parameter for an array of integers. So how do you write that? A formal parameter for an array of integers. How do I write that here? An integer array parameter. How do I write that? Int. Name of the array, let's just call it A. And then the brackets, right. So do we need another parameter? Yes. Why and what for? The size, yes, okay. Okay, so we're getting it. Okay, so what do we need to do inside the loop? The purpose of this function is just to increase the already existing values in that array. So we're not asking anything of the users or anything. Yeah?
Maybe use a for loop to go through each number and add plus 1.
Yes. We can use a for loop. We would use a variable I, and then we could say this. And then
A over bracket I plus 1 equal plus 9. So when I add 1, so just equal plus 9?
oh, no, it's just plus plus is what you mean. Yeah, that does it. That does it.
So my bad if I didn't get this earlier, but when you declare this parameter, the array has random values?
No. No. It's not the job of this function to populate the array. We might have another function fill-up that we've used that has gathered data from the user. We might have read the data from a file. It might have come from all different sources. It's not the purpose of this function to populate the array.
So A is just an array we already have.
Yes. Well, A is a parameter we will pass some array to it. When we call this function, we will call it maybe like this. Maybe like this. Yeah? Passing in an already existing array that already has values in it. Okay, good. So the next topic, well, before I continue with the next topic, are there any questions? Doubts? Nope, everything's fine so far? So programming with arrays, not that we have not programmed with arrays all the time. In this section we're going to talk, well, up to now, we have always assumed that we know exactly how many elements the array needs, and we need to work with all of those array elements. For example, we've assumed that there's a certain number of students, every student gets a score, and so we have to deal with all the elements of that score array. We've assumed that every plant needs to be considered every week in order for the production figures, and so our program had to work with all 4 of these production array elements. But in reality, it is often not the case that we know beforehand how many values we will have to deal with. Only in those examples that we picked, it was clear that we only needed that many. So it might happen that we don't know when the program is written how many array elements the array really needs. And one solution to this problem that we're going to look at now is to have partially filled arrays. The idea here is that we pick a size that we assume is going to be large enough for most cases, or maybe even all cases, in which the program will run. And then our program will use, or a run of the program will use only a certain number of array elements, as many as are necessary for that specific application of the program. And yeah, so that's the basic idea. What this requires is that we separate this idea of the array size into 2 separate concepts. One concept is the maximum size, the maximum number of elements that the array can hold, and the other is the actual number of array elements that we are using in this run of the program. Yeah? So previously, both concepts coincided when we looked at those examples. Now we're separating those concerns. Yeah. So functions dealing with the array may not need to know the declared size of the array. Those functions that do not add any additional elements to the array, they don't need to know the declared size. Those functions that only change existing values in the array, or that only read values from the array, they need to know only the number of elements used, not the declared size. Only those functions that add additional values into the array, only those need to know the declared size. So we will have a parameter number used for some of those functions. There might be functions that need both. There might be functions that need number used and declared size. There might be functions that need only declared size, and there might be functions that need only the number used, in addition to the array, of course. So the function fill array, called here, the function fill array, the way it is implemented, it needs both. It needs the declared size, and it needs the variable number used because it will set the value of the variable number used. So this here is a call by reference parameter. For my taste, a better way to implement this would have been to have it return an integer, which is the declared size, and then which is the number used, and then we would say number used becomes fill array and so on and so forth, and then but anyway, I mean that's just program style. Show difference doesn't need to know the declared size, it only needs to know how many array elements are used. And yeah. And I'm not going to go into the definitions of these functions. When the function fill array is called, we passed in a constant max number scores. Why does this make sense? Well, what would have been the alternative? The alternative would have been to use the constant max number scores inside the function fill array explicitly. Yeah? So, well, now I'm going to go to the implementation of those functions anyway. Fill array, where is it? Yeah. Starts down here, fill array, and we use size. We have a parameter size, and we use size here for this loop. Now the alternative would have been, instead of size at this point, to use max number scores, the constant max number scores. Why would that not have been such a good idea? One could argue I would have a parameter less, one less parameter. One could argue that that would simplify the program, but at what cost? It would make the function fill array able to fill arrays only of one specific size. The way it is now, with the function fill array implemented like it is, I could call it from one run of the program, I could call it several times for different arrays of different sizes. Yeah? For example, I would have two arrays, one called scores and one called counts, and then I would have two constants, max number scores and one max number counts. And I could call the function fill array with the array score and with the array count, passing the declared sizes of the individual array. If I would use a constant here, I would not be able to do that. So I have, there's a trade-off, right? We want to implement our programs in as simple a fashion as is possible. On the other hand, we also want our programs, the functions in our program, to be as generally applicable as possible in order to make the code reusable for future projects. And it can be argued that this additional parameter complicates the function just a tiny little bit while generalizing it substantially, making it more generally applicable. And then that's why it's a good idea to do it. So this is the key point. This makes fill array easier to be used in other programs. But be careful. This goal of making a function, making it easier to use a function in another program, that's not self-serving. You still want to have as simple an implementation as can be, allowing for a little bit of complexity, I mean, a little bit of complexity if it buys you a lot of generality. Okay, we're going to leave it at that for today. See you Friday.